Okay, so in this video we're going to get back to physics and get back to solving problems with Newton's second law. But before we do that, I just briefly want to talk about how to multiply a scalar and a vector. Now, we've been talking about vector addition, how to add vectors, and there's a way to multiply a vector by a vector. Actually, there's two different ways to multiply vectors by vectors, and we're not going to talk about either of those. Normally, they would be covered in a pre-calculus class or IB math, but they took it out of the IB math curriculum, and so unfortunately, that'll have to wait for another day. But we will talk about how to multiply a vector and a scalar, because it all comes back down to Newton's second law. Okay, that's why we've been doing all this stuff with vector addition, because Newton's second law is F net equals ma, and so if you think net force, by its definition, that is the sum of the forces acting on an object. That is basically the resultant vector of all the forces acting on an object. Okay, so that, by its definition, involves vector addition. And that is equal to mass, which is a scalar, times acceleration, which is a vector. Okay, and so all of this stuff we've been talking about links together. Okay, and so just really briefly, we're going to talk about this, but it won't take too long. Okay, so how do you multiply a scalar by a vector? So let's say you have a vector, let's just call it vector A, and let's say it has components 4 and 16. Units don't matter, it's just some generic vector. Okay, what is meant by the vector 4A? Okay, well, this is going to be very obvious, but basically what we're doing is we're multiplying a scalar 4 times a vector A, which in this case has components 4, 16. And so the vector 4A would be still a vector, but it would have components 16, 64. And that's it. Multiplying a scalar by a vector is that simple. Now, what does that mean exactly? Well, it's kind of what you would expect, actually. Okay, so remember, a vector has both magnitude and direction. The vector 4A is pointing in the exact same direction as vector A. The only difference is you would draw it as an arrow 4 times longer. Okay, so in other words, multiplying a scalar by a vector, all it does is change the length of the vector, but not the direction. Okay, now, what about the vector negative 2a? Well, negative 2a, the same rules still apply. You're basically multiplying negative 2 times vector a. And so that would still be a vector, but it would have components of negative 8 and negative 32. And in that case, what we've basically done is we've built a new vector, vector negative 2a, and this vector points in the exact opposite direction as vector a, and it's twice as long. Okay, and so multiplying by a scalar and a vector is very intuitive, it's very simple, and the rules for doing so are very easy to understand. You're basically just distributing the scalar to both of the components. Okay, that's it. Now, what does this have to do with physics? Well, remember that when you talk about Newton's second law, F net equals ma, net force and acceleration are both vectors. Okay, and so that means they have components. And so net force, you can think of, F net x and F net y. We've done that many times before in the last unit. Likewise, acceleration is also a vector, and so you can think of acceleration in terms of its components, ax and ay. Okay, and so if you write F net equals ma, which is Newton's second law, if you write that, as a vector equation, basically what that means is you have F net x, comma, F net y, that's net force, is equal to mass times acceleration, which is ax, comma, ay. But we just saw on the last slide what happens when you multiply a scalar by a vector. You basically just multiply each of the components by that scalar. And so this would be equal to max, comma, may. In other words, what I'm saying is that when you think of Newton's second law, because net force and acceleration are both vectors, you can basically think of it as two separate equations. You can think of it as F net x equals max, and F net y equals may, which is exactly what we've been doing for the past unit, and so that shouldn't surprise you at all, but I just wanted to show you how it works mathematically. Okay, so because net force and acceleration are both vectors, you can basically think of it as, you know, 2 or 3 separate equations. Right now we're only doing 2 equations. If you were taking this class in college, you would have, you know, a z equation also, like F net z equals maz, but we don't do the z direction at the high school level typically. Okay, so let's get back to doing some physics. So this unit, we're looking at advanced second law problems, okay, for lack of a better term. And we're going to look at the following types of problems: forces applied in 2 dimensions at an angle, inclined plane problems, pulley problems, and 2-object problems. Now, in general, the process for doing all of these second law problems is the same. You draw a free body diagram, you write out your second law equations, you determine acceleration on the right side first, and then on the left side you write out the sum of the forces before you plug in any numbers, and you do all that just to get everything set up, and then you start plugging numbers in after that. Okay, the only thing that makes these advanced second law problems any different is some of them have different tricks to them. Okay, but besides that, it's the same basic process for all of these problems. Okay, when you're doing pulley problems or 2-object problems, you have to do the second law process for each object involved. For inclined plane problems and pulley problems, you have a different coordinate system you have to use, but fundamentally they're all the same type of problem. Okay, so we're going to start off by looking at forces and angle problems. And here I just kind of wrote down the steps again in case you did not have them in your notes already, which you definitely should, because, well, it was a main part of the last unit. Okay, but these are the second law problem steps that we've been following for the past, like, month and a half. Okay, so forces at an angle. Okay, so again, same process, but now we're going to add something to it. Okay, so take a look at example 1. Example 1 says, a boy tries to pull a crate, which has a mass of 200 kilograms, across a rough surface by pulling on a rope, which is 30 degrees above the horizontal, with a force of 200 newtons. However, the crate does not move. Okay, so before I even look at the question, I'm going to, draw my FBD. Okay, so crate, he's trying to pull on the crate. I know the crate is on a surface because it says so. So I got force of gravity going down. Okay, I got normal force going up. And at this point, by the way, you might be questioning why this arrow is shorter than this arrow. That's intentional, by the way. You'll understand why in a second. It also says he's pulling on a rope, which means there's tension, but he's pulling on it 30 degrees above the horizontal. And so I'm going to draw that like so. Here is FT, and that makes an angle of 30 degrees with the horizontal right here. Okay, but the crate does not move. Now, why does it not move? Well, that means there must be static friction acting on it. Which way is the friction acting? Okay, now think about this. He's trying to pull it, and I realize he's pulling it at an angle, but imagine this in your mind. Just because he's pulling at an angle doesn't mean the box is actually going to move at an angle. Okay, because it's on a surface, and so even if it starts to move, it's only going to move to the right, which means the force of static friction would be acting to oppose that, and that would be to the left. Okay, so FFS is to the left. Now, I write out my second law equations. Keep in mind, at this point, I haven't even looked at the questions yet. I am just following the second law process. Same steps we've been doing for the last unit as well. And I know step 2, I need to determine acceleration. Because the object is not moving, because it is at rest, that means the net force is 0 in both the x and the y direction. Okay, if an object is at rest, the net force is 0. In this case, it's completely at rest. It's not moving in the x direction or the y direction. So both of these are 0. and then I write out the sum of the forces. You must write out the sum of the forces before you plug in any numbers. Okay, now what force is acting in the x direction? Well, there's two forces. Clearly we have the force of static friction. But we also have tension. But be careful, because if you look at the force of tension, tension is not acting completely in the x direction. But a part of it is. Which force is acting in the x direction? Well, it is the part of tension that acts in the x direction, aka the x component of tension. And so when I'm writing out the sum of the forces, the other force in the x direction is Ftx. Likewise, when I write down the sum of the forces in the y direction, I have three forces in the y direction. I have Fn, Fg, and I also have this other force in the y direction, the part of the tension that is going up, Fty. Okay, and so now hopefully you see why I drew Fn, the arrow for Fn, shorter than the arrow for Fg, because Fn and Fg are not equal in magnitude. Fn is actually less than Fg, because there's a third force in the y direction, Fty. Okay, so now I'm done with my three steps. Now I look at the questions. The first question says, determine the force of static friction acting on the crate. Because I did my setup, because I followed the process and I did my three steps, this is a very easy problem now. I'm asked to find FFS. I know if I find FTX, FFS plus FTX equals 0, so clearly those two must be the same number. Okay, so to find the force of static friction, all I need to do is find FTX. But that's basic math, because I know Ft is 200 newtons, and so FTX would just be 200 times cosine of 30 degrees. By the way, where some people will get messed up on this problem is they'll start trying to think, oh, okay, coefficient times the normal force. Well, we're not given the coefficient of static friction. We could find the normal force, and we will in just a second, but we're not given the coefficient of static friction, but we don't need it. Remember, the way static friction works is it is less than or equal to μs times Fn. In other words, it can equal any applied force you give it up to that threshold. In this case, we're going to be below the threshold, because it says the crate does not move. Okay, so Ftx is 173.2 newtons, so that means FFS plus the 173 equals 0. I'll put the 0.2 in there. And so FFS equals negative 173.2 newtons. And we're done with the first question. But now the second question asks us to find the normal force. And again, because I have the setup all done, this is a very easy process. I'm asked to find Fn. I can find Fg really easily, because Fg equals mg. And so that would just be 200 times negative 10, which is negative 2,000 newtons. And Fty I can find because, again, that's just basic vector math. Fty would be 200 times sine 30 degrees, and that would be 100 newtons. Okay, so Fn plus negative 2,000 plus positive 100 equals 0. And so Fn is going to equal 1900 newtons. And that's the answer to the second question, and I'm now done with example 1. So this is a very basic forces at an angle problem. And once you account for the little new bit of the forces are at an angle, and so you have to worry about components of those forces, these problems are really not any different than the ones you've seen before. Okay, Fn is a little bit less than Fg, because you can think the boy is pulling up at an angle, and so his pulling up allows the normal force to decrease. And we saw this on the soap opera friction worksheet in the last unit, where we had students fighting over a backpack, and you know, if you push down, you increase the normal force, and if you pull up, you decrease the normal force. And it's the same type of problem, except now the force pulling up is not directly up, only a component of it is. Okay, so pause there if you need to look at that some more. Now let's take a look at example 2. Okay, example 2 says Mr. Walker pushes a book with a mass of 2 kilograms up against a wall with an applied force of 50 newtons, which is directed 30 degrees above the horizontal. Assuming that the book doesn't move, calculate blah 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 blah. I will look at the questions in just a second. And by the way, I'm still keeping it relatively easy here for the most part. The object is at rest. That's going to make our second law equations easier. So here's the book. And let's draw this FBD because that's always the first step. We have the force of gravity going down. We have the normal force coming out from the wall perpendicular to the surface. Okay, we've done this type of situation before. The only new thing about the situation is now the applied force is at an angle 30 degrees above the horizontal. Okay, now I have to be careful, and in fact there's a chance I could even make a mistake. Now here's why. In the past we've done this problem and I've been pushing directly into the wall. And if I push directly into the wall, that means that the book is trying to move down because of gravity. And so the force of static friction would act up to stop it from falling down the wall. That's what we've done in the past. But the problem is now I'm pushing up at an angle. And so now, depending on how the math comes out and how the numbers work out, the book actually might be trying to move upward, in which case the force of static friction would act down. And I'll be honest, I don't know how it's going to turn out without doing the calculations. And so I'm going to say for now that the force of static friction is acting up, and I could be completely wrong, but I can always go back and change that. Okay, so let me write my second law equations and we'll see how the numbers work out. Okay, FBD is done. Again, I'm not even looking at the questions yet, I'm just following my process. Step 2, I want to write up my second law equations, and I want to determine if the object is accelerating. The answer is no, it is not accelerating in the x or the y direction, and I know that immediately because it says it doesn't move. An object at rest has a net force of 0 because of Newton's first law. Okay, so 0, 0. And step 3, I write out the sum of the forces. I forgot to label this. This is FA. Now, what forces do I have in the x direction? Well, I have Fn, obviously. And I also have the x component of the applied force, which I'm going to call FAX. What forces do I have in the y direction? I have FFS, I have FAY, and I have FG. Now, to be honest, I'm not sure whether FFS is in the positive or negative direction. We'll have to see how it works out in just a second. But regardless, those are my forces. That is the sum of the forces. Okay, so let's see how this is going to work out. Now that I'm done with the process, I look at the questions. First question says, calculate the normal force acting on the book. Okay, so I look down, I see, okay, Fn plus FAX equals 0. So all I really need to do is find FAX, and that will give me the normal force. FAX, based on the picture, would be the applied force of 50 newtons times the cosine of 30 degrees. And so that's going to be 50 cosine 30. That's going to be 43.3 newtons. And so Fn would be negative 43.3 newtons. Now, of course, if you had drawn the picture the other way, Fn would have come out to be positive 43.3 newtons. It doesn't really matter, to be honest. Normally, these questions are really just focusing on what is the work correct, and is the magnitude of the normal force correct. Okay, so that's the first question. Now, the second question is asking for the force of static friction acting on the book. Okay, so Fg I can find pretty easily. Fg equals mg. And so that would be 2.0 times negative 10. That would be negative 20 newtons. And Fay I can find because that would be 50 sine 30 degrees. And that would be 25 newtons. Plugging that in to find FFS, which is what we're asked to find in the second question, I get FFS plus FAY, which is 25, plus FG, which is a negative 20, equals 0. So let's see, 25 and negative 20 make 5, so FFS equals negative 5 newtons. Now, at this point, I realize, well, crap, I must have made a mistake at the beginning because I just found FFS is acting in the negative direction, which means my original FBD was a little bit off. In fact, the force of static friction is also acting down because I'm trying to push the book up. In other words, FAY is bigger than FG, and so the book is trying to move up, and so static friction is going to oppose that, and so really FFS should act down. And there's no way to have known that without doing the math, because I easily could have had less applied force, and the numbers could have worked out so FFS was acting up. Yeah, so this is one of those problems where it just depends on the values you're given, whether FFS is up or down. Okay, in this case, it turns out the force of static friction is actually acting down. Okay, so pause there if you need to look at that some more. Okay. Example 3. Let's see. We have a mass suspended from a rope and a ceiling with 2 ropes. Rope 1 is horizontal and rope 2 makes an angle of 30 degrees with respect to the horizontal. What is the tension in rope 2? Okay, so this one is going to get a little tricky. And so we're going to apply Newton's second law for this point right here. And as always with any second law problem, you should always start with an FBD. In this case, it's very simple. I have force of gravity going down. I have 2 ropes, which means I have 2 different tensions. I have FT1 in rope 1, and I have FT2 in rope 2. And without worrying too much about what the question is asking, I'm going to keep following my process, and I'm going to write out my second law equations. Okay, so F net x equals MAX, and F net y equals MAY. And we are lucky once again. It's not always this way, I promise you. But because this object is suspended, that means it is remaining at rest. That means, once again, the right side of these equations is 0. And it does not have to be that way. You can easily have a forces at an angle problem where the object is moving and it is accelerating. It just so happens that the 3 examples we've done so far, that's not the case. Okay, so, but in this case, because the object is suspended from 2 ropes, but the right side of the F net x equation and the right side of the F net y equation are 0. And now we write out the sum of the forces. In the x direction, we have 2 forces. We have Ft1, and we have Ft2x, the x component of Ft2. And we have 2 forces in the y direction. We have Ft2y plus Fg. Okay, now I look at the question. What is the tension in rope 2? Okay, so there's a few different ways to do this. I'm going to start with the easy way, and the easiest way is just to say, okay, well, I don't know Ft1, so this equation right here does nothing for me. Ft2, on the other hand, is balanced out by Fg, and Fg I can find in 5 seconds. Fg equals mg, yada yada. The mass is 20 kilograms, it's right there, times -10, so Fg equals -200. And so right away I get Ft2y equals 200 newtons. Now, that's not the same thing as Ft. It's not the same thing as Ft2, but it gets me what I need. Now, here's why. Because I know that, hypothetically speaking, I don't know what Ft2 is, but I do know the y component is 200 newtons, and I also know that the angle is 30 degrees. And I also have been doing vector components enough to realize basic trigonometry at work here. And I can use basic trig to say, okay, sine of 30 degrees is 200 over Ft2. And so Ft2 would be equal to, just rearrange that, 200 divided by sine 30, and that would be 400 newtons. Okay, so the answer there is A. Okay, and then if I wanted to, I could go on to find ft2x, and then that would get me ft1 as well. Okay, so you have to think a little bit about that one, but it's still not that difficult of a problem. Okay, so pause there if you need to look at that some more. Okay, let's see if we want to do one more problem. Let's see. Actually, I think I can probably do both of these other examples in class. That should at least give you an idea of how to get started on your forces at an angle worksheet. I do want to remind you that your test is coming up really soon, and that's going to include vector addition, and it's also going to involve problems with forces at an angle. As always, please let me know if you have any questions, and I'll see you guys in the next video.